All right. Okay. All right. So the second axioms is what we call as linearity. Linearity. So for the linearity, all right. So for the linearity, there exists a scalar value alpha, okay, and then it is multiplied with vector u, and then you have the inner product of that vector with the v, then this one can be rewrite as equal to alpha u v. This is for the case of multiplication. For the case of addition, okay, let's say we have this alpha, but then now it appears as a addition, then we will have the u plus alpha v, then the linearity of this inner form, it can also be rewrite as u vector u vector v plus vector alpha and vector v. Yes. Okay. So far any problem? Any question for this part? For the linearity case, under this axiom, for this case, it happens in the first component. If you notice, the inner product, it must be in pair. Okay, like you see in the notation here, it must has u and v. Okay, so the u we call it as the first component, and the v we call it as the second component. So for the second axiom here, it happens in the first component, the component u. Alright, so this is for the axioms. For the axioms number 2, for the linearity. Axiom, the last axiom, what we call as a positive definiteness. Definiteness, yes. So for the third axioms, it shows that, it mentioned here that the inner product, whatever field it is, whatever happen it is, the inner product must give a positive value. All right. So in this case, for the third axiom here, okay, for the third axiom here, okay, if let's say we have inner product of V with itself, this one, it must be a triangle, label there. It will be must be greater or equal to 0. The inner product will be equal to 0 if the vector is 0. Okay, it makes sense there. All right. Okay. All right. So this is for the axioms. Okay. We have another part. Okay. Another part from axioms. We call it as remarks. And for the remarks, it will help us to answer our question. What happened? For instance, let's say for the linearity. For the linearity, I mentioned just now, the alpha have occur at the first component. Is it possible for the scalar value or the alpha here to be exist in the second elements? So to answer that question, that is why we need remarks. Okay, so for the remarks, actually for the remarks, I did ask you to try it during the class last 2 weeks, okay, if you still remember. So, and we have tried together for the remarks number 2 and remarks, yes, for the remarks number 2 last time. So I hope by now you still keep with you the proof, okay, the proof to show that when the scalar occurs in the second component, by using the axioms we can prove it. Gitu. Okay. Okay ke setakat ni? Any question? Any question?
Okay, Doktor.
Okay, alright, good. So now we have actually settled with the definitions and the property for the inner product. So now we will look into the operation. Okay, so I do understand by now you might ask yourself why you need to know these things, why you should know the proof. Okay, kalau boleh guna nombor, kenapa nak kena buat proving? So it's actually whatever you have learned before in the mathematics subject during your school time or during your matriculations, that will be more on the application. So for this time, I will try to introduce to you the fundamental concept of all the calculation. Okay, alright. So now we will look into the examples. Okay, when I say example, it is not in a number context. Okay, it will be more on the different field or different types of numbers, numbers that happens in inner product. Okay, so for the fields, when I say fields, it can be real number, it can be in the form of polynomial, it can be in the forms of functions, in the forms of matrix, or yeah, that's all. Yalah. Okay, so we will look into the first example where the inner product occurs in the real numbers. Okay, so let's say V, okay, V, this one, let's say the V is the real number. Alright, so this is the notation of the inner product, right? So this operation, the operation for the inner product for the vector x and vector y, for the case of n equal to 1. Okay, let me repeat. The first example here is for the real number, and real number we can denote it as Rn. Betul? So it can be denoted as Rn. Rn. Okay, and this n can be 1, can be 2, can be up to n dimension. Okay, so let's have a look what happens or what are the operations for the inner product when the dimension is 1 or the n is equal to 1. So let's say we have our field V, and this field is for the R1. Okay, where n is equal to 1. Alright, so our inner product, we will get our inner product as x, y equal to multiplication of vector x and y. Alright, okay, so this operation here, we can say that the inner product of xy equal to xy defines the inner product on R1. Okay, alright, so what happens if we have if we generalize, now we have the n equal to 1. So let's say we have n equal to n. What will happen? So our field will be Rn. Okay, so our vector x, so we will have vector x as x1, comma, x2, and then x3, x4, dot, x, n. Alright, this is for our x. What happened to our y when it occurs in field Rn? So our y is y1, comma, y2, comma, y3, y4, dot, y until yn. Okay, so the inner product of these two vectors will be x, comma, y is the transpose of x, we multiply it with y. Alright? Okay, so if when we do the transpose here, then we will get the x1, x2 until xn, xn, we multiply with the vector y until yn. Then what we will get? We will get x1 multiply with y1, alright, plus x2 multiply with y2 plus dot plus x and y n. Alright, so this form here, when the field occurs at n dimension, if you observe here, this one, this presentation here, the n dimension here is similar to this one. Apa tengah kelas? Kelas. This one is similar to this one. Alright, so we continue, we proceed to this part. Alright, so this one, the n field here, we can simplify it to summation of I equal to 1 until n xi yi. Okay? So far so good, everyone? Okay ke? No. Alright, good. So, and if you notice in the notes that I have uploaded in to the Putra Blast, you can refer to slide number 9. So the slide number 9 has also showed the same notation as this. So this is how you get the summation of this is how you get this formula lah. Okay, so we start with the n equal to 1 for the one dimension first. We get this first notation and then we expand it into n dimension. Then we will get a sequence of multiplication of vector x and y. Hence, this is the operations that happens or occur for the inner product for the case of real number. Okay, so from this, from the summation I equal to 1 until n x I y I, if you apply back this one, whatever you got this, and you can prove actually this is fulfill the axiom, these three axioms. Okay, so you can try to do that if you want. Okay. Okay, I will try to show you for the symmetry first. Okay, so I will try to I will show to you that this notation here actually fulfill the first axiom, the symmetry axioms for the case of real number. Okay, so we have this, the summation here. Ya Rabbi, banyak. Set dah. Sekejap nanti bilang pula. Okay. Okay, alright. So for this one, okay, we have this what we call just now, we have this axiom for the case of field of real number n dimension. Okay, so we have this x okay, and this one is summation of I equal to 1 until n, and it is x I y I. Okay, so we look back into the first axiom, the symmetry for the real number. It says that the inner product of the vector uv is equal to the inner product of vu. All right, so let's check here. This summation here will give to you the x1 y1 plus x2 y2 plus dot plus x and y n. Right? So now what happened? Okay, let's say we compare, we do the comparison. We have the inner product of vector u and vector v. All right. So now this vector for the case of R n. Okay, for the case of Rn. So our y, our vector y is this. Our vector x is this. So if we want to find the inner product of vector u and v, then we will have y, vector y transpose, we multiply it with vector v. Vector v. Apa vector V pula kan? This one vector X. Sorry. This is vector X, not V, X. So if we do the, I repeat, so now we try to do the comparison between the inner product of xy and yx, okay, in the field of Rn. Okay, so looking back to this one, the first one, the R1. So this is basically the operation like I said just now, right? So for the y, for the inner product of yx, then we will get the transpose of y we multiply with matrix x. Okay, so from here we will get y1, y2 until yn, and then we will multiply it with x1, x2 until xn. Then when we do the operation here, we will get y1 x1 plus y2 x2 plus plus yn xn. Alright, I will stop here. So now if you try to compare these two operations here for the inner product of xy and the inner product of yx here, this one and this one, it looks similar, right? So the operation of inner product for the xy is similar with the inner product of yx for the field of real number n, okay, and dimension. Hence, we can say that for the case of real number field, okay, the inner product of x, y is similar or equivalent to y, x. Okay, clear? So, if we look back to the axiom here, it's actually fulfilled. We are actually successfully prove that the inner product of xy is equivalent or is similar to yx. Okay, so if you do the second axiom here, okay, by adding the alpha to the x, then you will definitely will get this one. Okay, so for that, I want you to try on that for that part proving. Okay, so now your task is, your task is show axiom 2. Okay, this axiom 2. So try buat Ikutlah masuk dalam exam ke soalan ni kan. Alright, so try to prove this one despite sana. Okay, any question? Anything to ask? No. Yes or no? Okay. If no question, I will proceed to the next example. Okay, so just now, in this slide 3, I show to you the example for the real number, the operation. How are you going to calculate? If let's say you have a problem and that problem exists in a real number field, then how are you going to do or how are you going to calculate? So basically, you just do the summation of I equal to 1 until n xi, yi, and the x and the y are the vectors, are the provided or the given vectors. So maybe I can give you this one is for the vector, this one is angle. Let me give you example lah, so that easy for you to understand. Okay, okay, this one. Okay. So, second. Okay, let's try this example here. Okay, so remember you have one task. Your task is to show the axiom number 2 for the inner product for the case of real number. Okay, fine. And this is another example. Okay. So this is the a numbering example here so that it easy for you to understand. Okay. So now you are given 2 by 1 yes 2 by 1 vectors for the x and for the y. So what are the inner product for these vectors? Okay. So now you need to find the inner product for these two vectors. So you have x okay, and you have vectors y. So remember the inner product for the two vectors, okay, is for the case of real number is equivalent to summation of I equal to 1. In this case, your n is 2. Okay, and it is x, I, y, I. Alright. Okay, so in this case, you can say that this xi is 2 minus 3 here.
Sorry, Doctor.
Yeah.
Doctor share screen ke?
Ya Rabbi, patah. Okay. Alright. Okay. Sekarang nampak tak? Nampak
Nampak, Doctor?
Okay, good. Alright. So now, this is the example, the numbering example, so that easy for you to digest whatever I explained just now. Okay, because the previous one is just a variable. So you mungkin tak dapat nak nampak dia punya apa operation dia tu sebenarnya macam mana. Okay, so this is awak nak buat macam ni. Okay. Sana. Macam ni. Okay. So for this one, this is the, so now we want to find the inner product of these two vectors, the x and the xi, the x and the y. Okay, so now you are given 2 by 1 matrix or a 2 by 1 matrix lah, ataupun this, for this case is the vectors. So in this case, it's 1 until 2 kan? Alright, and then for this one, it is 2 minus 3. Remember this one, kita kena transposekan dia. 5. 5, 1. Okay. So in this case here, if you want to expand this operation, it will be 10. 2 times 5, 10 plus minus 3 plus minus 3 multiply with 1. So here, oh yelah, oh sorry. Sorry. So okay, 2 times 5 we get 10, and then plus minus 3 times 1. So here we get minus 3. Okay, so the inner product for this vector is 7. Ini tak ada dah. Ini kurung management. Okay, is 7. Alright, so this is basically the operation, the operation for the R2. This for the case of R2. Okay, alright. Example lain. Okay, I think yes, I think that will be for the real number. So now we move into the next example where the field is matrix. Okay. Your internet connection is unstable lah dulu. Okay, tak apa. Alright. So for this case, for the matrix, there are two cases. First is when the dimension of the matrix is n by n, or it has the same dimension. The second case is when the dimension of the matrix is different. Okay, is different. So I will show to you the case where the dimension for the matrix is n by n first. Alright, so for this one, let's say your V is your matrix. Okay, your matrix, and your matrix has a same dimension. Alright, mn over real number lah. Okay, alright. So how are you going to get the inner product of this matrix? Okay, so in this case, let's say you are given two matrix A and matrix B. Okay, and these two matrix has same dimension. Okay, meaning that let's say A 2 by 2, then B also 2 by 2. Gitu, alright. Okay, so in this case, to get the inner product for this matrix, with this dimension, we will use what we call as trace. Trace of matrix A and B transpose. Alright, so remember, for the inner product, the end product must be a scalar. Okay, but in matrix, if you do the multiplication for the matrix case, you will get matrix. So based on what you have learned so far for the matrix, which operation can help you to turn the matrix product into a scalar product? Kita ada buat hari tu, masa hari Isnin hari tu, masa kita bincang soalan test tu, kita ada buat satu operation, and that operation is the input is matrix, but then the output is a number. Ingat tak apa dia? Perasan tak? Hari tu kita ada buat, dia ada kaitan dengan inverse. Inverse matrix, bila you buat, you dapat in a matrix, bila you buat inverse, you akan dapat matrix. Tapi ada satu operation, there is one step to get the inverse. Bila you kira tu, you akan dapat satu nombor je daripada matrix. Ingat tak? Apa operation tu? Anyone yang nak jawab? Anyone? Ada siapa nak jawab? Halo, ada tak ni orang? Ada tak sesiapa nak jawab? Haziq? Ada tak nak jawab? Ivan? Senyap je ni. Zahiruddin? Nak jawab? Zahiruddin? Ingat tak? You ada buat operation matrix. Kita ada input dia sebagai matrix, and then keluar dia tu sebagai satu-satu nombor je. Ingat tak apa dia? Awak semua ni tambah online senyap je ya. Kita cari, bukan dari sini.
Doktor,
Ya saya.
apa nama benda tu ke sana?
Apa nak operation tersebut? Operation tu yang dia boleh mengubah matrix kepada scalar number. Ingat tak? Dia ada operation tu berlaku ketika kita nak dapatkan inverse matrix tersebut. Operation
Determinant.
Ya, betul. Determinant. Yes, correct. Yes. Kenapa lah tak jawab pada awal? Kenapa soalan saya tadi macam berbelit Saya minta maaf tapi betul lah jawapan dia. So, from the determinant process tu, if you notice, from matrix, you boleh dapat a scalar value. Kan? So, that will be one way actually for you to do the inner product for matrix. But I am not going to use that approach. Okay, so I am going to introduce to you a new approach, lah hopefully kan, to get the inner product for the matrix, which we call it as trace. Gitu. So from the trace pun kita boleh dapatkan a value, one value from matrix. So what is the trace? That will be a question. Trace ni apa dia? Apa operation trace ni? Trace ni basically is the summation of the diagonal matrix. Okay? So, trace is a summation of a diagonal matrix. Okay? Okay tak? Alright, so for instance, let's say we have this matrix. Contohlah saya rasa kalau saya bagi example nombor ni awak lagi mudah nak ingat, lagi mudah nak nampak. Let's say we have matrix A. And matrix A, the first element is 10, the second element here is minus 10, the third element is 5, and this is 2. Okay, so in this case, for this matrix, the diagonal, so if you notice, this matrix is n by n dimension. It is a 2 by 2 matrices, 2 by 2 dimension, gitu kan? So, in this case, the diagonal for the matrix A, the diagonal for this matrix is this. Susah pula kita. Is this one 10 and 2. Hence, what is the trace for this matrix? So the trace for the matrix A is 10 plus 2, which is 12. Gitu. So this is a trace. Okay, the summation of the diagonal matrix. And this one, the inner product of matrix A and B is equal to trace A B transpose. This one is only applicable for the n by n dimension matrix. N by n. Kalau n by m by n tak boleh. Okay, sebab m by n dia punya row dah lain. Row dia lain daripada bilangan column dia. So we cannot get the diagonal. Yang diagonal inilah. Diagonal yang ini kan. Yang ini. Okay, clear so far for that one? Any question? Any question, guys? Boleh tak? Okay tak?
Okay.
Okay, good. Okay, I will show you proving je kan. Kalau matematik ni dia memang proving saja. Okay, sebelum tu, again, I do understand you tak faham, you mungkin terfikir-fikir, bukan tak faham lah, mungkin you terfikir-fikir kenapa kita nak kena, I mean every time bila saya introduce operation je kita kena buktikan. It is very important. It is important actually because we already have that theory, remarks, axiom, kita dah ada semua tu. Tapi sekarang ni you kena faham, you kena tahu macam mana daripada axiom tu ataupun daripada theorem tu kita boleh buktikan. Maksudnya theorem yang ada tu dia menyokong apa sahaja operation yang ada. Sebab sometimes daripada satu basic theorem ataupun teori yang you belajar, you boleh kembangkan dia kepada teori lain. Okay, sebab tu you kena tahu properties, axiom, theorem, matematik tersebut. So that you boleh manipulate. Kita bukan tipu tapi kita manipulate. From one basic, kita boleh extendkan dia untuk jadi lebih complicated. So itu yang daripada situlah knowledge expansion berlaku. Okay? So sebab tu saya perlu untuk tunjuk. Mungkin awak tak faham sekarang, it's fine. Tapi at least you pernah dengar dan you pernah tengok benda tu. Alright? Okay, so saya proceed. So for this one, so now we are going to show to you this one. Okay? Dan this proving step ni pun dia ada kaitan dengan axiom yang awal-awal tadi kita tengok. Okay? Alright. So in this case, kali lah. Okay, so now we have this. This is what are given to us. The matrix A, okay, and this is what are given to us. A, B. Okay, alright. So from the matrix operation, gitu. Kita ada sikit lah kat sini matrix operation. Yang ini ada kat dalam nota ya. So daripada matrix operation, we do know that from here, from matrix operation ataupun matrix property, kita tahu bahawasanya the multiplication of matrix A and B transpose is equivalent to matrix B transpose multiply with A transpose. Ni property pertama. Okay, the multiplication of matrix A dengan transpose B is equivalent to transpose B, matrix transpose B multiply with matrix transpose A. Alright, so another properties of matrix with the transpose is A transpose. When we add another transpose here, it will be equivalent to A. We have the matrix transpose A, we do another transpose to that transpose matrix A, we will get the first matrix, the initial matrix. Alright, so from this matrix property here, so now we can have the trace, and then in this case we will take this part, the first matrix property here to here. No. This one, the first step is we will put in the first property ni ke sini. Okay, and at the same time, okay, by imposing the second properties for the matrix to here, we will get something like this. Okay. T. Sekejap okay lah. Ni kita ada ni lah, sediakan confuse pula. Betul. Okay, alright, and hence from here we will get so from here, then we will use another property here, but this property is not the matrix property but the trace property. So the trace of A is equivalent to trace AT. T. Yes. Hence, here we will get trace B A B A T. And this one from here, it will give us, if you notice, this one is B transpose A, and the first one is A transpose B. Hence, this one is actually equivalent to inner product of B A. And by using axiom, so this one, by using axiom 1, okay, A, inner product of matrix A is equivalent to matrix B A. Okay? Okay ke? Okay ke semua? Pening sikit. Okay ni insyaAllah okay. Okay, so this is for the case of matrix. Matrix So we look into the next. Before I proceed, any question for this part? Yes or no? Before I proceed to the integral part. This is just I will just introduce some part for the integrable. I will just introduce itu. Okay, so if no question, then I will proceed for the next example. So we have looked to the case of real number and then matrix. Matrix pun for the apa tadi tu, for the n by n. Okay, for the case of matrix m by n. Okay, m by n. For the matrix m by n. Okay, I will just share to you for the case of matrix, this one. I will just share to you the sana. Okay, so this is the formula that you can use for the case of matrix with dimension m by n. Okay, so basically what you are doing here is you just multiply this row here, 2 minus 1, 3 and 1, 8. Yeah, you will just multiply the first row of the first matrix with the first row of the second matrix. Okay, and this is the formula here, which you can use for the algorithm lah sebenarnya. This formula we can use for the algorithm. So we will settle the inner part first, then it will be controlled by the outer layer here. Alright, so this is for the case of matrix m by n. Okay, this is the formula, and this case is for the n by n matrix. Okay, alright, so I am not going to do the proving for this part. So this part complex. Alright, okay, so any problem, any question? Yes or no? No, senyap semua. Okay, tak apa. So now I will show to you the next example for the vector for the integral vector space. So let's say we have a field of this let's say this vector is the vector space of integrable real valued functions on A to B. Okay, so this is for the integral bukan polynomial. This is for the function space. Okay, so for the function space is for the integral. So let's say you are given two functions, all right, f and g. Hence, the inner product for the function f and g is this. This function happens over A and B, all right, and the function is function f and this. Okay, so this is the inner product for this function. It is the integrable operations. Okay, there is another definitions. Okay, definition. So if you notice, when every time when I said the field, sometimes or most of the time I will mention this term, the vector space. Okay, the vector space here. So it is the vector space. So when the inner product happens to the vector space, that vector space we can call it as inner product space. For instance, let's say in this case, the inner product happens to the function. In this case, we have a vector space for function f. Okay, so when we apply the inner product to f and also to the function g, then now this operation, we can say that this operation happens in inner this space now become inner product space, no longer the vector space. It is a vector space, but because of the inner product operation happens here, now it becomes inner product space. Alright, okay, so now we have looked into the axioms, the remarks of the inner product. We have looked into the inner product. I hope by now you know what is the inner product, how to present the inner product, so on and so forth. So now we will look into how this inner product can be related to the norm or length and angles. Alright, okay. So can we rest for 5 minutes? Boleh ke?
Boleh.
Yeah. So if you want to go to toilet ke apa ke, bolehlah dulu ya.